We're now going to look at artifacts in ultrasound images. This is quite an important topic because artifacts occur very, very frequently in ultrasound imaging. In fact, you could say that every single ultrasound image contains some level of artifacts. Artifacts are therefore important because they are a limitation of ultrasound, but they're also important because they can potentially be useful at times diagnostically. In this and the following 3 lectures, I'll be talking about different categories of artifacts. And I'll start first by defining artifacts and why they occur. The term artifact simply means any appearance in the image which doesn't accurately represent the tissues that are being scanned. So, tissues may appear distorted in the image, they may be misplaced or missing, or duplicated, or various other sorts of distortion. Now, artifacts can at times cause misinterpretation of the image and therefore the potential for incorrect diagnosis. Obviously, we want to avoid this, and so it's important that you learn to recognize the major image artifacts, to know how to check that they are in fact artifacts, and perhaps how to minimize them if necessary. However, some artifacts are relatively unimportant and can simply be ignored, and some artifacts, such as shadowing, are actually diagnostically useful. So why exactly do artifacts happen? Most artifacts occur because the assumptions built into the way the machine creates the image are not correct. So in other words, the ultrasound isn't behaving in the idealized way that the machine has to assume. Sometimes inappropriate equipment settings can cause artifacts, and of course it's your responsibility to make sure that doesn't happen. Very occasionally you may have equipment faults or electrical interference causing artifacts. So what are these assumptions that I've talked about? The first is that the transmitted ultrasound beam is really just a narrow, straight line. We know that's not true. The beam has a significant width, perhaps several millimeters typically. However, the machine creates the image by placing all the echoes along a straight line, and so it's behaving as if the beam really was just a thin, straight line. The next assumption is that the ultrasound, both the transmitted and received ultrasound, travels straight along this line and don't deviate from it. That the ultrasound pulse always travels directly from the transducer to a given reflector or scatterer, and then the echo from that travels directly straight back to the transducer. This, of course, is built into the way the machine calculates depth. The machine assumes the propagation speed is 1540 meters per second in all tissues, and that attenuation is uniform throughout the tissues. And finally, and quite importantly, the machine assumes that all of the echoes that it detects are caused by the most recent transmit pulse. When this is violated, we get a particular artifact known as range ambiguity. Let's begin with a well-known artifact, shadowing, or acoustic shadowing. This occurs whenever we have a small localized area in the tissues which has a significantly higher attenuation than the other tissues. So this could, for example, be a calcification, an area of fibrous degeneration, a foreign object perhaps, plastic, metal, etc. On the left, I'm showing a table of the typical attenuation values in soft tissues, and you'll see that they range from relatively low values in liquids such as blood to somewhat higher values in the soft tissues, and then noticeably higher values in muscle. In the center, we have an example of a shadowing artifact. You'll see that we have a bright object casting a shadow. Now sometimes you can see the object causing the shadow, as in this case, but sometimes you can't. You just purely see the shadow. Now notice that the shadow is parallel to the ultrasound beam. This is, of course, exactly the same as if you have a shadow cast by the sun. The shadow will always be directed parallel to the sun's rays. This, of course, gives you an easy way to check if it is an artifact. You can move the probe around and see if the shadow moves so that it is always parallel to the beam direction. Now, what can we tell from looking at this image? What we can say is that the object causing this shadow has a higher attenuation than the other tissues around it. So we have an area of localized high attenuation. What we can't say from looking at the image is what the object is. We don't know if it has a high absorption of ultrasound or whether it's a strong reflector or what the reason is for the attenuation. We purely know that it is a strong attenuator. Now, as I mentioned, this is quite often a useful artifact. In this case, because it's drawing our attention to an object that perhaps we didn't realize was there. But another very well-known use of shadowing is in looking for gallstones. Gallstones cast significant shadows, and therefore shadowing can be a way of finding gallstones when there is a suspicion that they're there. Here's an example of shadow caused by something within the liver. On the left-hand side, the operator of the machine noticed the suggestion of a shadow in the center of the liver. You'll notice in this image that the focus is set deep in the image, which is what you would normally do if you wanted the entire liver to be relatively uniformly focused. However, notice on the right-hand side, when the focus depth is altered so that it is approximately at the same level as the object causing the shadow has become much more prominent. So focusing the beam on the shadowing object enhances the shadowing effect. So now we can see that unequivocally we have a shadow. Here's the reason for that. On the left-hand side, where the beam is focused deeper than the shadowing object, you can see that the beam is relatively wide at the level of that object, and therefore quite a bit of the energy in the beam bypasses it and isn't blocked by the presence of that object. And so it has a relatively modest shadowing effect. On the right-hand side, with the beam focused at exactly that level, the beam is of course much narrower, and therefore a much higher fraction of the beam's energy is being blocked by the object, and therefore we get a much stronger shadow. So this is a practical point whenever you're trying to determine if a shadow is real, or if you're using shadowing to look for something such as gallstones. Here we're looking at essentially the opposite effect. This is known as tissue enhancement, echo enhancement, or just plain enhancement. On the left-hand side, we can see a gallbladder casting a significant area of enhancement deep to the gallbladder. Again, this is going to be directed parallel to the ultrasound beam. Now, this is happening, of course, because when the ultrasound passes through the gallbladder, there's less attenuation than the machine is expecting, because the attenuation in liquids is low. And so the energy in the deeper tissues is stronger than the machine expects, therefore the echoes are displayed brighter than they should be. So enhancement is often useful in detecting the presence of fluids. Now, in the case of the gallbladder, it's obvious what's happening. Enhancement is neither useful nor really a problem. It's just simply there. On the right-hand side, though, we have an example of where enhancement can be very useful. In this case, we have an object casting a very bright enhanced region behind it. The thing that's distinctive about this is that the region causing the enhancement is filled with echoes. This might make us think that it was a solid mass, in which case it would be unlikely to cause enhancement like this. In this case, we're very tempted to think that this is liquid-filled, and therefore we have a cyst with some sort of particulate matter, it may be blood clot for example, causing an appearance like soft tissue within the cyst. So enhancement is a particularly valuable tool in differentiating between cystic and solid masses. Now this image also shows another artifact. Running down the edges of the enhanced region, you can see shadows. It's particularly noticeable on the left-hand side of the image. You've got a shadow parallel to the enhancement, lined up with the edge of the cyst. This is something known as edge shadowing. Let's take a look at it. Here are two other examples of edge shadowing. On the left, we have edge shadowing caused by the ultrasound hitting the edge of the gallbladder. And on the right, we have a testis causing edge shadowing. So you can see that edge shadowing can be caused by liquid-filled objects, solid objects, etc. But the common factor is always that you have a curved structure and the ultrasound is striking the edges. So it's just tangentially striking the edges of a curved structure, and this is causing a shadow. Hence the term edge shadowing. This diagram shows why edge shadowing occurs. So on the left, what we have is a cross-section of, let's say, a cyst, and the ultrasound is striking the wall of that cyst, and the beam is deflected. But the important thing is that the beam is being defocused. It's spreading out, it's becoming wider, and this automatically means that the intensity in the beam reduces dramatically because the same amount of ultrasound energy is being spread over a bigger beam, and therefore it's more diffuse. The intensity is lower. Lower intensity means that the echoes coming from that region where the arrow is pointing will be lower as well, hence the shadow. So edge shadowing is caused by the defocusing of the beam, not the deflection of the beam in another direction, but the defocusing. Now the machine doesn't know any of this is happening. It assumes the beam has continued on in a straight line, and so the shadowing is actually displayed in the image in a straight line where the beam should have gone, and therefore it starts at the edge of the curved structure and runs down deep into the tissues parallel to beam direction. So this is a classic appearance. Most of the time it's not at all useful because most of the time we can see there is a curved structure causing the edge shadowing. Occasionally it may be useful, but this normally falls into the category of artifacts that we will recognize and therefore know to ignore, but it's neither a problem nor useful. So in summary, I've talked about the meaning of the term artifact and the general causes, and in particular the imaging assumptions. We've looked at three examples of attenuation artifacts: shadowing, enhancement, and edge shadowing.